We are drowning in data, right? But how do we find the real story inside all that noise? Well, today we're going to look at a really cool field that throws out the usual charts and graphs. Instead, it's all about finding the hidden shape of the data.
So let's just start with this big question. Imagine you've got this enormous data set. I mean, it could be anything. Stock market data, DNA sequences, maybe readings from a huge sensor network. How in the world do you find the actual story in there? How do you pull out the signal from all that noise, especially when the patterns are anything but obvious?
Because, a lot of the time, our data just looks like this. A big, chaotic cloud of points floating in space. Your standard bar chart? A line graph? Yeah, they're not going to cut it here. They're totally blind to the real underlying structure. The loops, the empty spaces, the hidden connections that are actually telling the story. So, here's what we're going to cover. First, what is this hidden shape? Then, how do we even get from a bunch of points to a shape? We'll look at how to find the patterns that really matter, what the final fingerprint of the data looks like, and then, of course, where this is all being used out in the real world. Let's dive in.
Okay, first things first. Let's tackle the basic problem. What's the big deal with just having a cloud of points? And what new angle does this topological data analysis thing even bring to the table?
So what exactly is topological data analysis, or TDA for short? Well, at its heart, it's a bunch of really smart mathematical tools. But here's the key. They don't just count stuff or try to fit a line through your data points. Nope. TDA looks at the fundamental shape and structure of the data itself. It's all about finding these really solid qualitative insights that pretty much every other method would just completely miss.
But wait a second. How do you get a shape from a bunch of totally disconnected dots? That's the big question, right? And this leads us to the real aha moment of TDA. It's this fundamental shift in how you look at things that makes the whole idea click.
I love this analogy. Think about it like this. TDA is telling us to stop staring at individual stars in the night sky. Instead, it's saying, hey, step back a bit. Look for the constellations. We're not interested in the points themselves, but the larger patterns and shapes they make together. It's a total shift from the tiny details to the big picture structure.
And the process is actually way more intuitive than it sounds. It's basically like a super sophisticated game of connect the dots. So, step 1, you start with your cloud of points. Step 2, you start connecting points that are close to each other. You make lines, then you make triangles, and you keep going. And then, the final most important step, you keep track of which shapes pop up as you slowly change your definition of what counts as nearby.
Okay, but that last step is everything, right? I mean, how do we know which of these shapes are real patterns and which are just random noise? This is where the absolute genius of TDA comes in. It's an idea called persistence.
The best way to get this is to picture it. Okay, imagine we put a tiny little ball around every single data point in our cloud. Right at the beginning, these balls are super small, so nothing's touching. Every single point is basically its own little island. We'd call that a connected component.
Now here's the fun part. We're going to slowly start growing all of those balls all at the same time. As they get bigger, they're going to start to touch and overlap. And when they do, our little islands start merging. But something really cool can happen. A bunch of balls might connect in just the right way to create a hole, a loop, right in the empty space between them. And at that exact moment, poof, a new topological feature is born.
And if we keep making the balls bigger and bigger, eventually that hole we just made gets completely filled in. The loop vanishes. And at that moment, we say the feature dies. So think about that. Every single feature, every island, every loop, every void, it has a birth time and it has a death time.
So this whole process, tracking the birth and death of all these shapes across all these different sizes, that has a name. It's called persistent homology. And really, it's the engine that makes TDA run. It's methodically writing down the lifespan of every single structural feature that shows up as we look through every possible connection distance.
Okay, so we've done all this work, we've grown the balls, we've tracked every loop and every island. What's the payoff? What do we actually get out of this? Well, what we get is a really simple but incredibly powerful summary of our data's true shape. All of that growing and tracking boils down to something we call a barcode. And it's exactly what it sounds like. It's this simple, elegant visual summary. It's like a unique topological fingerprint for our data set. And reading one of these things is super easy. Each line, each bar in the barcode is one of those features we found, like one of those loops. The place where the bar starts, that's when it was born. The place where it ends, that's when it died. So pretty simple, right?
The length of the bar is just its lifespan, how long it persisted. And this right here is the whole point. The long bars, those are the important ones. They represent features that stuck around for a long time, across a whole bunch of different scales. These are the real robust structures, the true shape of the data. And the short little bars, they just flickered in and out of existence. They're basically just artifacts of random chance. It's what the researchers called topological noise.
And this is the core value, right? It's a way to separate the signal from the noise. The foundational paper puts it perfectly. TDA helps us distinguish between information and what is sometimes called the topological noise. That persistence, that lifespan, is the filter that lets us finally see what's really going on.
So this is a pretty powerful idea, you have to admit. But is it just some abstract thing for mathematicians? No way. Let's talk about why this actually matters and where people are using it like right now.
And the applications are just wild. They're all over the place. We're talking about material science, where it's helping to discover brand new compounds. In biology, people are using it to find hidden patterns in huge genomic datasets. It's even being used for things like analyzing brain activity or understanding the structure of massive sensor networks. It's everywhere.
So, the big takeaway should be this. TDA isn't here to replace things like machine learning or stats. Not at all. It's a partner to them. It's a totally new lens, a new way of looking at your data that can show you things that were completely hidden before, all by focusing on this idea of a robust, multi-scale shape. Which leaves us with a pretty cool final thought, doesn't it? If every complex system out there, from the stock market to the climate to even the human brain, is generating data that has some kind of hidden, meaningful shape, what other amazing discoveries are just sitting there, waiting for us to finally put on the right pair of glasses to see them?